All right. So now that we have understood, when we are given an IID sequence, what are the different things that that we can characterize about it? We can characterize the sample mean, the sample variance. There is a concept of degrees of freedom, and then there is also statistical inference, which is very interesting. Which gave us an idea that Z bar could be an erroneous understanding of, of mu, and you may want to, rather than rely on this point estimate, go forward one step forward and evaluate a confidence interval, which is for a given level of probability or that you are likely to see Z bar values in. So in the previous lecture, we figured out a 95% interval, confidence interval for the IID case for Z bar, which was Z bar minus 1.96 sigma hat over root n and Z bar plus 1.96 sigma hat by root n. So the confidence interval was in these bounds, right, with the lower and the upper bound, right? So now we generalize this IID case a little bit. How do we generalize it? We introduce spatial dependence to the data, right? So we introduce specifically a metric or a measure of spatial dependence, which is spatial autocorrelation, which we have articulated on this slide as covariance of pairs Zi and Zj for our given data set is given as sigma squared rho to the power I minus j in absolute terms, right? So the absolute value of I minus j is in the exponent, and I can go from 1 to n, right? So now this gives us two distinct cases. One is when I is equal to j, that is when, let's say, we are talking about covariance of Z1 and Z1. Now covariance of Z1 and Z1 is nothing but just the variance of Z1. This definition says that it's going to be sigma squared rho 1 minus 1, which is sigma squared rho 0, which is just sigma squared, right? And you can evaluate for any I case where I is equal to j, right? So I can, in general, I can say covariance Zi equals variance of Zi is going to be sigma squared root to the power 0, which is sigma squared for all I goes from 1 to n. So the first thing it tells us that the variance of Zi's is exactly the same, which is sigma squared, right? So I'm still working with an identical variance, case. But what is happening is that, what happens is that as soon as I have I is not equal to j, right, we have, let's say we have covariance, for example, 1 and 2, we have variance, it's going to be sigma squared rho absolute value of 1 minus 2, which is just 1. So we have sigma squared rho. If I look at covariance Z1 and Z3, I will have sigma squared rho absolute value of 1 minus 3, which is sigma squared times rho squared. And then covariance Z1 and Z4 will simply be sigma squared root cube, and you can keep going. Covariance of Z1 and Zn will be nothing but sigma squared rho n minus 1. Right? So now what's happening is that I have a distance metric sitting on the exponent of rho, right? So typically we say that rho is between 0 and 1, right? And it's an important condition. We'll see at some point in the course later, and we come to the idea of stationarity and all that, that rho, if it is higher than 1, it can have major consequences on what can be done with the data. Well, we'll see that we can't really do much. But anyway, for now, we'll just take rho to be between minus 1 and plus 1. And the idea is that, when I take any position in space, let's say position 1, Z1, I can have, when I move to Z2, there is some dependence between Z1 and Z2 given by a multiple of rho. As I move farther away from Z1, the dependence, goes down at an exponential rate by rho squared, rho cube, and all the way to rho to the power n. Okay, so when I'm given my data set, right? So when I'm given this data set, right? So data set, let's say the data set can be ordered from Z1 to Zn. So I'm going to simply just put location. So this is a real space, right? So location 1, location 2, location 3, location 4, keep going, you have till location n, right? And the idea is at each of these locations you have data Z1, data Z2, Z3, Z4, and Zn. So these are realizations on space. The idea is that the value that I realize on Z1 has a dependence metric that specifies the spillover effect of location 2, spillover effect of location 3, spillover effect of location 4, and so on and so forth. Similarly, realize that I also have covariance of Z2 comma Z1 is also sigma squared rho 2 minus 1, which is equal to sigma squared rho. So the idea is there is also a spillover in the opposite direction for all the values. Of course, as the distance sort of increases, the strength of the spillover declines. So strength of spatial dependence goes down. Now, instead of this real space being visualized as as some kind of in a spatial sense, I could have also thought of it as a time dimension. So in case of time, you had time period 1, you had time period 2, time period 3, time period 4, and time period n. And there also we have this understanding of autocorrelation, temporal autocorrelation, where value at t2 has a spillover from t1. Similarly, t3 has a spillover for t from t1. I mean, it also has a spillover for t2, and so on and so forth. The only difference between spatial autocorrelation and temporal autocorrelation is that in case of time series data, the spillovers do not go back. So the idea is because in time series, time is unidimensional and unidirectional, what happens is that value that is realized at t equals 4, cannot have any effect on what happened in t equals 1 because t equals 4 didn't even happen then, right? So it necessarily will have only, the effect will only be one way, that is the value that has happened in the previous period may have an effect on what is happening in the current period. But what's happening in the current period could not have had any impact on what happened in previous period just by the virtue that it happens on a later date, right? So this unidirectionality is relaxed in case of spatial dependence or spatial autocorrelation, right? So here the dependence, unlike in one direction, that is increasing time periods in case of time series data, also comes back. So every entity has a spatial impact on every other entity with a strength which is given by rho to the exponent of distance between those entities. Okay, so having understood this interpretation of this the spatial autocorrelation structure that we are working with, now let's go forward and evaluate different characteristics of this distribution. Okay, so I'm going to say note that Zi's are still normally distributed with mean, mu, and variance sigma squared. However, now let's say these entities are no longer independent. So I still have an identical distribution, but they are not independent to each other, right? So what happens at Z1 is impacted by what happens at every other location, and whatever happens at every other location is impacted or is dependent to some degree on what happens at location 1. So this is interesting. This is a very complex structure if you really try and visualize it, start to visualize it, right? And remember, we are only working in one-dimensional space right now. If we go beyond one dimension and we look at say 2 dimensions or 3 dimensions, you can imagine the math will really become complex, and that's the point, right? We can still work with those things in fairly simplistic, with fairly simplistic, tools. So that's the point, that we will sort of see pan out in future, in future lectures of this course. So we are working with entities which are no longer independent, and of course we still care about the mean. So what is the mean, the sample representation of mean mu? So I'm asking the same question. I'm asking the same question that I asked in the IID case, which was to say that, what is the best guess of mu? Well, at the end of the day, what information do I have? I mean, my information that I have is I have a sequence Z1, Z2 till Zn. Of course, they are spatially dependent, fine, but that's the information that I have. So my best guess of mu is still going to be Z bar, which is nothing but take every value, weigh it equally by 1 over n and just sum it. Okay, so again, even when you have spatial dependence, the best guess of mu or mu hat is equal to Z bar, right? So Z bar is indeed the best guess. The data may be independent or spatially dependent. Now what changes, right? What changes, is variance of Z bar is going to change, with respect to the IID case. Okay, and to evaluate it, let's try and move forward, right? So let's see. So we want to evaluate the variance of Z bar, because we know it's a random variable, it's composed of random variables. There is an error, I want to articulate that error, and that error will come from variance of Z bar, and I want to get there, right? We want to evaluate variance of Z bar. So before we do that, what I'm going to do is I'm going to sort of try and go back to where we started, right? So we had articulated the variance of Z bar as variance of 1 over n summation I equals 1 to n Zi, and I said 1 over n squared, and we had written this as summation I equals 1 to n variance of Zi plus 2 covariance of Z1, Z2 plus 2 covariance of Z1, Z3, keep going, plus 2 covariance of Zn minus 1, Zn, right? So we need these pairs of covariances to be part of this variance definition. In case of IID, the covariance terms were all zeros. In case of spatially autocorrelated data, they are all non-zero. So this yellow, the terms within yellow curly brackets are no longer zero. In fact, we are given a definition of those, and that is covariance of Zi and Zj, right? So we know covariance of Z1 and Z2 is sigma squared rho. We know covariance of Z1 and Z3 is sigma squared rho squared, right? So what we are going to do is we are going to introduce a variance covariance matrix, which is a very concise tool of encapsulating these covariance terms in at one go. So covariance of Zi and Zj, I'm going to write this in a variance covariance matrix. So I have n data points, So I am going to have a n by n variance covariance matrix. So I have n rows and n columns. The diagonal elements are going to be sigma squared. So each row is representing i's, which is 1, 2, 3, all the way till n. And each column is represented by j's, which is 1, 2, 3, all the way till n. So I have n rows and n columns. What happens is that given my definition, so the definition that I have is that covariance Zi, Zj is equal to sigma squared rho absolute value of the difference between the locations I and j, such that I goes from 1 to n and j goes from 1 to n. So I am going to use this definition and fill in the variance covariance matrix. Quite clearly, the diagonal elements are going to represent the variance terms when I equals j, right? So I is 1 here and 1 here. I is 2 here and it's 2 here. I is 3 here and it's 3 here. Similarly, I is n here and n here. So all the diagonal elements are going to be just sigma squareds, right? So sigma squared, I'm just going to use dot 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 for you to understand that all the diagonal elements are nothing but sigma squareds. Now let's come back to the off diagonal elements. The off diagonal elements are, so what is this off diagonal element here? This represents covariance Z1, Z2, right? The covariance Z1, Z2 we have seen previously is equal to sigma squared times rho. What about this element here? It is sigma squared rho to the exponent absolute value of 1 minus 3. So I have sigma squared rho squared. Similarly, I will keep going. I will have sigma squared rho to the power n minus 1. Okay. What about this element here? This is covariance of Z2 comma Z1. And this 2 will be nothing but sigma squared rho given my definition. And I'll have Z2 and Z3 again sigma squared rho because the distance between 2 and 3 is still 1. So sigma squared times rho. And you keep going, you have sigma squared rho n minus 2. Right? For the third row, which is third I, 3 and 1 sigma squared rho squared, 3 and 2 sigma squared rho, keep going sigma squared rho n minus 3. Okay? And then we keep coming down. Okay, so we have here n and 1, so sigma squared rho n minus 1, sigma squared rho n minus 2, sigma squared rho n minus 3, and keep going. Okay. Similarly, you can fill all of these values, and the point that I'm trying to make here is that the off diagonal elements are non-zero. In fact, they are a representation of spatial dependence. By contrast, if you were to consider the case of IID, what would happen? Okay, so as an aside, we are just going to quickly look at the case of IID. The case of IID. So in case of IID, if I were to sort of, get to this variance covariance matrix for the IID case, I will still have the elements in the diagonal of this, cells of these matrix, which will be equal to sigma squared, sigma squared, sigma squared. And again, I have i's 1, 2, 3, all the way to n in the rows and j's as columns all the way till n. But what is different between the variance covariance matrix in case of spatial dependence or spatial autocorrelation as specified with the rho parameter is that while in that case, in the case of spatial dependence, off diagonal elements are non-zero. In the IID case, all of these off diagonal elements will be just zeros. So right, so we have a much simpler case where everything is zero, right? One last thing I want to point out with the variance covariance matrix is that it is symmetric, right? So you will see, if you see sigma squared rho here, you see a mirror of it here, right? If you see a sigma squared rho n minus 1, you see a mirror of it on the downward side of it as well, right? So the left and right of the diagonal are symmetric. So the variance covariance matrix is always symmetric, right? So it is sufficient to just write down the any one side of it, and the other side can be automatically filled in because we know that it is a symmetric tool. So with this understanding, with this understanding of how to articulate the variance covariance matrix, ultimately our aim is to figure out the variance of z bar, and we want to fill in these values of where we want to put in the variance terms and the covariance terms and so on and so forth, right? So basically what I am doing is I am summing everything, each cell of this variance covariance matrix, I am summing it and I am multiplying it by 1 over n squared, okay? So when you do that, what you're going to get is variance of z bar is equal to 1 over n squared. We can also take out sigma squared, by the way, right? So in the previous on the previous page, I could have taken sigma squared out. I could have taken sigma squared out as a common multiplier from each cell of this matrix, right? So I can just take sigma squared out and I will be left with 1s in the diagonal elements, and off diagonal elements will be rho squared, rho to the power n minus 1, and so on and so forth, right? Okay. So here what we are going to do is we are going to also take out sigma squared. So I'm going to have sigma squared over n squared, and inside I have n plus, so all the 1s in the diagonal elements are being summed. I get an n. So this n is nothing but the sum of all the 1s in the diagonal elements of the variance covariance matrix plus twice of n minus 1 times rows. So there are n minus 1 rows, n minus 2 row squareds plus n minus 3 row cubeds, and you keep going. You have 3 root to the power n minus 3s, you have 2 root to the power n minus 2s, and you have a 1 singular row n minus 1. Okay, so so remember we have taken this twice, this 2 multiple out, so all of these are occurring twice of times what you are writing here inside the square bracket. Okay, now this sum can be rewritten as the following. So I'm gonna take out this sigma squared by n squared multiplied by n plus 2 sigma squared by n squared times you have n times rho plus rho squared plus rho cube, keep going, plus rho to the power n minus 1 minus rho times rho plus 2 rho squared plus 3 rho cube plus n minus 3 rho to the power n minus 3 plus n minus 2 rho to the power n minus 2 plus n minus 1 rho to the power n minus 1. Okay, sorry about that, little fumble there. Okay, so now it turns out that this first series is nothing but a geometric progression. Okay, so we have rows just increasing geometrically as a sequence. So you have rho squared, rho cubed, rho to the power 4, all the way till rho to the power n minus 1. So you have a sum of a geometric progression, right? So it's a geometric series, and this one which is deducted from it, from this geometric series, is an arithmetic geometric series, right? So it's a combination of an arithmetic progression and a geometric progression. And it turns out that we have these standardized, formulae for summing a geometric progression as well as an arithmetic geometric progression. So I'm going to simply apply these. You can go and recall. I'm just going to put a recall. You should go back and check how to write down the sum of a geometric progression. So sum of n elements that are, characterized by a geometric progression. And you should sum, you should go and figure out what is the sum of n elements that are characterized by a arithmetic geometric progression. I'm not going to solve these, so, provide these. You can check it in any standard, mathematics text. And you can use this to then write down the variance of z bar. You can simplify it as sigma squared 1 over n plus 2 over n rho 1 minus rho to the power n minus 1 divided by 1 minus rho minus twice 2 over n squared rho plus rho squared 1 minus rho and minus 1 over 1 minus rho minus n rho to the power n. Okay, n minus 1, and that's it, which can be then approximated as, let me write it here so that it's clearer. We write it below, sigma squared 1 plus rho over 1 minus rho times n. Okay, so now let's go back and let's go to the next page and then contrast between the IID case and the case where we have spatial dependence characterized by the rho parameter. So we have a spatial autocorrelation scenario or case where covariance of Zi and Zj is given by sigma squared rho modulus I minus j, and the other case is we have spatial I equals 1 to n and j equals 1 to n, where if we have spatial independence, right? So we have seen these two cases, which is nothing but the IID case, right? We have seen this, and we have just seen the both the cases, right? So spatial dependence and spatial independence. So IID and spatial dependence. Now in the spatial autocorrelation case, my variance of Z bar, it turns out to be sigma squared 1 plus rho over 1 minus rho n. Okay, I'm just gonna write sigma squared over n multiplied by 1 plus rho over 1 minus rho. And in case of the spatial independence case, this variance of Z bar was simply sigma squared by n. So in order to contrast them, what I can do is I can rewrite variance of Z bar in case of spatial autocorrelation as sigma squared over n prime, where n prime is nothing but n times 1 minus rho over 1 plus rho. Clearly 1 plus rho, which is a denominator which will be higher than 1 minus rho, right? It is going to be definitely higher. That means n minus will be definitely less than n. N prime will be definitely less than n. So what we are seeing here is that the case where you introduce dependence in the data, right? The variance of Z bar, the way you articulate the error in Z bar, right? The error or the variance in this random variable Z bar is using a denominator on sigma square, which is n bar, which is an equivalent of spatially independent values of data, right? So this is equivalent spatially independent data. Okay, so what happens is, because of dependence in data, there is similarity in data. And what happens is that on the net, we have only n prime spatially independent values instead of the n values that we are actually looking at, because there is dependence in data. It compresses, or it kind of reduces the data size to an equivalent n prime size, which is obviously less than n in terms of, evaluating the variance of z bar. And what will happen is, because n prime is less than n, variance of z bar will be higher when you have spatial dependence relative to when you did not have spatial dependence. And that's because that basically says there's going to be higher error. There's going to be a different error in how good a guess is z bar of the population mean, right? So what we are actually saying is that statistical inference, right? So this will imply that statistical inference, right? Statistical inference was the bound of z bar values, the bound of z bar, the confidence interval of z bar will now be different, right? So now your will be different than in the IID case, right? More specifically, in the IID case, the 95% confidence interval for z bar was given as z bar minus 1.96 sigma hat over root n, comma sigma bar, or z bar plus 1.96 times sigma hat over root n, and you have a lower and upper bracket, round bracket. In case when you have spatial dependence such that covariance zi, zj is equal to sigma squared rho I minus j for I1 to n, j1 to n. I'm writing it again and again because I'm talking about this specific example. This is not the most general answer. This is for this example so that we understand the consequence one step at a time. So spatial dependence, which is given as covariance zi and zj, it gives me, here the 95% confidence interval for z bar will be given as the lower bound z bar, which is exactly the same as the IID case, minus 1.96 sigma hat over root n prime. Okay, this n prime is lower, so I have a bigger bound on the, I have a smaller lower bound than in case of IID, and a higher upper bound than the IID case, right? So I'm trying to draw your attention to the point that you have a n prime in the denominator, which is different from n, and n prime is less than n, right? So where n prime is strictly less than n. Okay, so now, I'm going to end this lecture with a small exercise. So I'm going to say class exercise, and then we will end this lecture. We will come back and review this in the next lecture, because it's been a little bit of a involved material today. So say you have a sequence of data z1, z2 all the way to zn, where n is given as 10. Okay, n is given as 10, and there is spatial autocorrelation with the same structure as our example in this class, but with rho given as 0.26. Okay, we have to evaluate an equivalent of independent observations for the given case, right, the given spatial dependence case, that is, I'm asking you to evaluate n prime, and consequently the new 95% confidence bounds for Z bar. And I want you to sort of go over this exercise, and then we will evaluate it, we will solve it in the next class. Thank you for your attention.